If we have a similar situation where we have a suspended mass over a pulley accelerating another mass, but this mass is sitting on a frictionless plane, like a frictionless tabletop, or maybe it's a cart with very low friction wheels, that would work as well. Then what are the forces acting on our system? Well, we certainly have the 5 Newton gravitational force acting downward on the 500 grams. Now there's going to be a tension force here and a tension force here, but the tension force is internal to the system. Over here, we didn't consider the tension forces in looking at the acceleration of the overall system. Tension forces are internal. Now here we analyzed the tension force, but to do so, we broke this mass out of the system and just looked at it separately. Okay, so there are tension forces, but they're internal to the system. And we can, of course, analyze the tension forces, and we do. Okay, you have the gravitational force acting downward, and of course you have to have a normal force acting upward, or this downward gravitational force would accelerate this block through the incline, through the tabletop. We assume the tabletop is strong enough to withstand this 20 Newton downward force. Also, so we have a normal force, and the normal force is going to be great enough to make this thing levitate up off the table. So the normal force turns out to be equal and opposite to the 20 newtons, because there's no other force acting. Now if there is some other force pushing this down into the incline and maybe pushing it forward or backward at the same time, then our normal force would be different. Okay, but that's not the case. Okay, so this leaves a net force of -5 newtons. Gravitational force here is balanced by the normal force. It doesn't, then there's no contribution to the net force. The only force acting then is the gravitational force here. And then in this case, the acceleration is going to be net force divided by total mass. Total mass is the 500 grams and the 2 kilograms. That's half a kilogram and 2 kilograms. We divide the net force by that total mass and we get the acceleration -2 meters per second squared. Where implicitly we haven't really stated it, and we should have. Well, yeah, actually we did state the positive direction, again being counterclockwise, because we have two masses moving in different directions, but they're accelerating the same. So the system is in a clockwise rotation where the positive direction is counterclockwise. Now the tension is the net force on the isolated 2 kilogram mass, so we can easily get that. Again, the only force that's accelerating this mass is the tension force, so we easily find that the tension is 4 newtons, multiplying the 2 kilogram mass by the 2 meter per second squared acceleration. And this is, of course, the magnitude of the net force. It's 4 newtons, and if we want to be complete, we'll say it's 4 newtons to the right, but we just express tension by its magnitude, okay? There's a 4 Newton tension pulling the ends of the string together. And now again, the tension in both ends will be the same as long as there's nothing in between that exerts a force on the string. And a light frictionless pulley, of course it does exert a force on the string, but it doesn't exert a force in the direction of the tension, in the direction of the string. All the forces are perpendicular to the string all the way around this pendulum, this pulley, and the same is true here. So that the tension in both ends is the same. That means that we're going to have an upward 4 Newton tension here, okay? And let's see. The net force here is going to be 1 Newton. The net force up here is 4 newtons. Or the acceleration is going to be the same. Well, where you've got 4 times the net force, you've also got 4 times the mass. Think about that. That verifies our result. Okay.